Hi, welcome to part 2 of how to do inference for slopes. And we're talking through how the sampling distributions work. Part 1 was we kind of did an experience about how that was all set up if somebody was assigning students a place to sit in class. And so we're going to go through the formalization here, walk through it, talk through some things, and then get you guys set up for confidence intervals and significance tests. If you haven't had a chance yet, make sure you go down below, like, comment, subscribe. And we will continue to do this. As I said in the beginning of the other one, I am redoing my 3-week AP test or AP exam review course. So that'll be done by the 9 different units, and we'll talk through all of that. So those will be ready probably here within the next week. So moving over here, we have sampling distribution for B. There's really 3 parts to it. The first one here is the population is mu of y is equal to alpha plus beta x. Alpha and beta are going to be, alpha is obviously the population. We'll talk about it over here actually. So alpha is the parameter for the y-intercept, which we'll be using here as in the sample of A. And that, oops. That's what I want, sorry. So alpha corresponds with A, beta corresponds with B, which is going to be our slope here. And there's 2 other things that you'll see in the data. We're going to go through what's going to end up happening for most of these. We're not going to be running any calculations ourselves. We're going to be given the data output from a computer program, typically called Minitab, but you could look some other ways, and so we'll show you how that's set up. And a lot of times these will be multiple choice questions, occasionally a free response question. You will see S, that corresponds with sigma, that is the standard deviation of the residuals, like what we did back in Unit 2, the typical distance that each piece of data is away from our model, and then our standard deviation for slope, which will be sigma B, and then go from there, okay? And then from there, we'll go through and have, the other part of here is just what the typical setup is. So what the typical setup is here, you've got the sampling distribution of B. And then, so what we have here is, so then it's going to be a normal curve. So we say it's normal. 0 is going to be our mean in the middle. And then we've got our standard error of B there as well. Okay. So the example that we're going to go through here is, you may have heard about how noses, ears don't stop growing. And what actually ends up happening is it's just gravity dragging on the cartilage and stuff. So what ends up happening from there is, so we go through and we sample 30 adult noses, or ears height, I'm sorry, and measure how high they are. So we take their age and their ear height. And so this is the data that we end up seeing from it. So you get all of these numbers out through here. And so remember, we're trying to tie it back to y hat is equal to a plus bx. Y hat indicating that it's a sample. Age is going to be your x value because, again, x is going to be explaining, the age is explaining the years, not the years explaining how old you are, or not how big your ear is explaining how old you are. And so because of that then, so the constant is going to be your y-intercept because the constant doesn't have anything doing with it, right? The part of the linear variable that has the variable is going to be your slope. And so that means it's going to be with the age. So x is the age. So here your slope is 0.0021. We'll talk about defining that here in a second. And then up over here, you're going to see, actually I should probably grab this. So up over here, we have your a value. So that coefficient, so the number out in front of your constant, so in this case it's just your constant, is 28871. And then you got the 2 other standard errors over here. Notice down here we have r squared and r, just like what we did back in chapter 2. You might be asked about it, you might not. And then T and P, you're not going to have to worry about it at all. Down over here, S is the standard deviation of the residuals. So in a problem like this, so eventually we are going to do some calculations. Those are all listed on your formula sheet. We're going to talk more about that in confidence intervals and significance tests. So for right now, all we're going to do is interpret this. So when I ask you for what's an estimate for alpha, alpha and A match up. And again, this is a different alpha than you have for your the significance test levels, okay? So this is the alpha, this is the population mean, population value for your y-intercept. So this is your y-intercept, and so your description here is going to be people aged 0, so in other words, newborns, okay? For people of age 0, their predicted ear height would be 2.8871 centimeters, okay, on average. And again, it's the predicted value because, again, we're talking about the least squares regression line. Least squares regression line does predictions. The population values are going to be the actual ones, or the data values are the actual ones, okay? So similarly, when I ask for an estimate for beta, we're going to use B, which is the slope. So it's going to be the 3613, or the 0.0021. And that interpretation is going to be for each increase of 1 year. And that's going to be important when you're saying this. We're going to predict an increase of the ear height to be 0.0021 centimeters. And again, it's predictions. So we're just saying, is when you're going back to the line, remember the line is the prediction, your data is going to be off of that, and that's why we have residuals. So when they're asking for sigma over here, we're going to use our S value that we have off of our data up here, so the 0.3613, and we're going to say that is the actual ear heights typically vary. And remember that phrase we haven't used pretty much since the beginning of the year. So the actual ear heights typically vary about 0.3613 centimeters away from the predicted value of the ear height. So again, how far off that line are we? And then last but not least, the standard error of the slope. And this is going to be one of the newer parts. So we're going to say the slope of the sample least squares regression line typically varies about 0.0059 centimeters per year. Make sure you use that, since we're talking about slope, make sure you use a slope-ish context from the slope population of least squares regression. Okay? So anyway, that brings us to the ending of our third from last lesson. So we only have confidence intervals to go through and significance tests to go through. Those obviously are things that you know how to do. So we're going to tweak them for the slopes of least squares regression line. So it's going to be a lot of things that are going to be familiar. We're going to have to tweak some of our formulas. So we'll talk about those the two next times. So make sure, again, you have a chance to take a look at what we're doing. Over here will be a place for you to subscribe. And over here will be part 1 of this lesson. So if you want to go back and kind of get a feel for how things are working, you can do that. We'll see you soon.